So today is the last real material-wise class. On Thursday, we will do a brief recap. And the new homework is out. The final exam is out there. Let's see if you can look at the. Let's spend a bit of time to look at the final exam papers. So there are 3 papers that you can work on. This first paper is a paper from the journal Science, which is really what the whole chapter 7 of Chandler's book is based on, the one about liquids. So it's an old paper, but it's quite interesting. It goes through a lot of things. And this WCA model, this weak Chandler-Anderson model, is a very popular model to study liquids. And it's one step further from what you have done in chapter 7. So this is one paper. The second paper is regarding free energy perturbation. It's from Journal of Medicinal Chemistry, where people talk about how Zwanzig's relation is actually used to design better drugs and things like that. And so this is a very practical paper. The third one is very interesting too. It might be more complicated, perhaps in some sense, but it's a very important paper. This paper goes to those of you who like quantum mechanics. This is really a practical application of Feynman's path integral formalism to map a quantum system into a classical system. So the idea is that any quantum system can be mapped into copies, many classical particles interacting together through spins, and there is an isomorphism which becomes exact as you increase the number of classical particles. So if you like quantum mechanics, then I think you will like this paper more than the others. It's a very famous approach. This is called, it leads to a method called path integral molecular dynamics, PIMD. So this is a very, very interesting paper. It's long, but if you enjoy quantum mechanics, you might find this paper to be extremely, extremely interesting. And yeah, so you have these 3. You have to write a 2-page report and just make your report legible. You know, I gave some guidelines regarding font size, this and that. I didn't want to sound like specifying everything, but the whole idea being that write a report which is legible, still carries science, enough information about the paper regarding the figure. It can be figure about anything. Don't just put a bunch of words in the figure, but it should be a figure that summarizes what has been explained in the paper. And the report should be typed in LaTeX or in Microsoft Word or whatever you feel like. So any questions? Okay. So in this very last topic, we are going to continue to look at the Ising model as an example of systems that can undergo phase transitions with complicated interactions inside them. But in order to study Ising model, we are going to introduce very, very briefly something called renormalization group theory, or people also call it the RG theory. So renormalization group theory is something we could take a full semester to do. It's quite a lot of ideas that go into it. And for this theory, Ken Wilson received the Nobel Prize in 1982 in physics. He developed most of the ideas for renormalization group theory when he was a PhD student of someone also who got the Nobel Prize, I think, the name Murray Gell-Mann. Does anyone know what's Murray Gell-Mann most famous for?
Standard model.
Even more? I would say even more. Maybe you won't agree, but in my view, even more. What else is he famous for? It's related to standard model, yes.
Disagreeing with Feynman all the time.
Agreeing with Feynman is also good, I guess. But I think he predicted quark theoretically before they were invented. So this notion of a quark, which I said related to standard model. So Ken Wilson did most of this, but very close to, he's the only one who got the Nobel Prize. But Ken Wilson's ideas, if you read his Nobel Prize lecture, were really based on work done by Leo Kadanoff, who was at Chicago, and our own Michael Fisher, who is still here, he's still alive, but he's very old now, who, like I said, used to teach Chem 687 until a few years ago. He's in chemistry and IPST. And they did much of the work on this in 1960s, also along with Ben Widom at Cornell. So these are really the people who did most of the work. Over the decades, Ken Wilson was able to make it very practical, and of course, with his own ideas. And Wilson, Kardanoff and Fisher did get the Wolf Prize for this. They did not get the Nobel Prize. Nobel Prizes can be quite complicated and political, but they did get the Wolf Prize for this in 1980. So there is a lot of history about this. You can go and read up on it. And with all this history, what's the basic idea in real animation group theory? The basic idea in real animation group theory is that imagine a system which is made up of lots of little tiny parts. I'm drawing boxes here. This could be an Ising model. This could be something else. Some system made of lots of little tiny parts. And you could think about how this tiny part talks to this other tiny part, But now zoom out a little bit. Zoom out a little bit, and instead of looking at each box at a time, think about 4 boxes at a time. Okay? And think about how these 4 boxes talk to each other. Why stop there? Let's zoom out a bit more. Let's think about how 16 boxes talk to each other, set of 16 boxes, how talk to each other. So you can keep changing the scale as you go from a system where you're looking at every box at a time. You can zoom out a little bit. You can look at maybe 4 boxes at a time. You can zoom out even furthermore. You can look at 16 boxes at a time. The key idea in renormation group theory is that the physics of many systems is scale invariant. It does not depend on what scale you are using to look at the system. This is true almost all the time, which basically means that if I'm trying to describe a problem, centimeter and meter and kilometer kind of do the job depending on what the problem is, right? You could try to, so the units don't really matter. The numbers change, but the nature of the problem does not change. So the key idea in renormation group theory is to understand how the fundamental properties. So the main challenge here is that if these little boxes were interacting through some black interaction, and you zoom out and look at a blue box, they are interacting through some blue interaction. What is the relation between the black interaction and the blue interaction, right? That's the main challenge. That's the hard thing to figure out. Is it really the same, or does something happen to it? That's the issue. And we will look at it mathematically. How the fundamental properties and forces of a system vary depending on the scale of measurement. This is what we want to figure out. If we can find a connection between this, then instead of looking at a system made up of 10 to the power 23 number of atoms, we could zoom out, we could keep dividing it, keep decimating the system, so to say, until it's made up of very few things, or the interactions become very weak, and then use the properties of one system to infer the properties of some other system. That's what we are going to do. So how do the fundamental properties and forces of a system vary depending on the scale of measurement? And so in order to do this, what renormation group theory does is it decimates. Decimate means reduce, eliminate, right? It decimates or removes certain degrees of freedom to have a smaller system. Once you have such a smaller system, the challenge is, how do the interactions in this smaller system look like? Are they going to be similar? Are they going to be different? So the hope is that the interaction in the smaller system should be similar to what you had in the original bigger system. And so let's see how this works for Ising model. So all this kind of abstract sounding stuff will suddenly become clear as to how this is actually work. So we will look, and the renormalization group theory applies to many things, a lot of things. That's why, you know, Nobel Prize is not given to something when it's not applicable to many things, right? It is extremely applicable to problems from stock market to modeling the weather to looking at proteins to even deep learning. People try to understand how this deep learning works by looking at renormalization group. So let's look at Ising model, and I'm mostly going to do Ising model in 1D for this, where we know what is the answer. We know the answer is boring. We know the answer is that the Ising model in 1D should not have a phase transition. The critical temperature should be 0. Let's see how this comes out of renormalization group theory ideas also, and then I will give you a basic flavor for how it looks in 2D and gets the critical temperature right. For 2D, read a paper by Kardanoff in American Journal of Physics that I have posted on the website. That paper is a really nice paper where he talks about how to do this in 2D. So I really encourage you to go and look at it. But let's look at an Ising model in 1D with 0 external field. So for such a model, what is our energy term given by? We wrote down our energy term as E nu. And did I put a minus or not? Yes, I did put a minus. We put E nu is equal to minus. And we are going to look at nearest neighbors. So minus A minus J modulus equal to 1. J Si multiplied by Sj. Okay. So I want to write down the partition function for the system. There is no volume, there is only number and temperature. So the canonical partition function for this system, how can it be written? It will be going to all microstates and summing e to the power minus beta. This is basically the last class of the semester. We have just recap left. So at this point, you should be very familiar with what this symbol means, what I wrote down here. So partition function is summing over all microstates e to the power minus beta E nu. What is the meaning of all microstates? The meaning of all microstates means to go at every spin, S1, S2, S3, and look at them being plus minus 1. So in a system made up of n spins, this means 2 to the power n things go inside the summation. So now here I will have e to the power minus beta E nu. Now let's do one thing in order to simplify our math. Introduce k is equal to, so this beta times j, or j by kbt. Why do we do beta times j? Because look at this thing over here. We are going to multiply E nu by minus beta. We are going to multiply this thing with minus beta, right? So beta times j is going to show up all the time. So let's call this beta times j as a parameter k. So with this, so this is my equation number 2 actually, and this is equation number 1. We have the energy functional. So, and let's call k as equation number 3. So then our q can be written as not as n comma t, but n comma k. We have absorbed the temperature into k. J is just a number. J does not change. J is the interaction which we are keeping constant. So with this, the Hamiltonian can be written as S1, S2, S3, dot, Sn is equal to plus minus 1 e to the power minus beta multiplied by plus minus j. So that becomes a plus k. And now this is a summation inside, but we are looking at only nearest neighbors. So we can write it down as S1, S2 plus S2, S3 plus S3, S4 plus dot, right? I'm being sloppy about what happens at the end. So I'm just starting at S1, okay? So I'm assuming it's big enough. Does this make sense, this equation? Okay, so this is the full partition function. If we could get this partition function, if you could actually calculate it, then we could get all sorts of wonderful properties. This is going to be a hard thing to calculate. It's really complicated. So let's look at why it is so hard and what we can do about it. So let's consider our spins. They look like spin number 1, spin number 2, spin number 3, spin number 4, spin number 5, spin number 6, dot, dot, dot. Technically this side also dot, 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 but I'm going to be, yeah, so it's a huge number of spins. And each one of them can be +1 or -1, +1 or -1. So what renormalization group theory does is something kind of strange. It goes and removes all of the even numbered spins. How do you remove spins from an interaction? What does that even mean? Let's write it down in a moment. It will become very clear. So remove even spins. What do I mean by removing even spins? Well, in order to remove even spins, let's look at equation 4 once again. Equation 4 can be written as summation S1, S2, S3, dot, 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 Sn. By removing, I mean average over these spins. Just calculate what values they can take and explicitly account for them. So this is e to the power k S1, S2 plus k S2, S3, correct? S1, S2, S2, S3 multiplied by e to the power k S3, S4 plus S4, S5, right? I haven't done anything profound. Equation 5 is just writing equation 4 by changing the variables a little bit, right? Because if you look at this thing, what happened here? S1, S2 plus S2, S3 plus S3, S4 plus S4, S5, dot, 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 it's the same thing. Now we can do something else. We can just notice that S2 shows up in only this term, right? Everything else after this first one does not have an S2, right? S2 shows up only in this first thing. S2 shows up only here. Similarly, S4 shows up only here. And we know that S2 can take only two values, +1 and -1. Similarly, S4 can take only two values, +1 and -1. Now, there is nothing special about doing this to the even numbered spins. You could have done this to the odd number spins also. It won't make much of a difference. It's without loss of generality that we pick the even numbered spins, okay? So let me write down equation 5 again on the next page because it's so important. So we just wrote down that Q of n comma k is equal to summation S1, S2. Actually, let's write down this summation in the following form. S1, S3, S5, S7, dot, dot, dot is equal to +/-1. And S2, S4, S6, S8, dot, dot, dot is equal to +/-1. There's nothing wrong in that, right? I've just classified my labels separately. And in parallel, what we wrote down here was e to the power k S1, S2 plus S2, S3 multiplied by e to the power k S3, S4 plus S4, S5 e to the power k. What will I have next? S5, S6 plus S6, S7, and it goes on, so on and so forth. So this S2 that I have over here matters only for this first term. The S4 that I have over here matters only for this second term. S6 that I have over here matters only for this third term. And we are going to exploit this property. How do we exploit this? We say, well, S2 can take +/-1. So let's just write it down. Let's actually do the summation over S2, S4, S6. And then we will be left with only S1, S3, S5, taking the value +/-1. And this first term, the red thing, will become e to the power k S1 plus S3 plus when you give S2 the value +1, and when you give S2 the value -1, it will become e to the power minus k S1 plus S3. Okay. Similarly, for the second term, where we are going to do the same thing to S4, that will be e to the power k S3 plus S5 plus e to the power minus k S3 plus S5. Dot, dot, dot. So what did we just do? Let me write down this final equation. We have just shown that Q of nk, which we had written as S1, S2, S3 plus minus 1 e to the power k, S1, S2 plus S2, S3 plus S3, S4 can be written in an equivalent form. There is no approximation here where we are not summing over the even spins. We actually perform that summation explicitly. We are left with only the odd number spins. And then it looks like e to the power k S1 plus S3 plus e to the power minus k S1 plus S3 multiplied by e to the power k S3 plus S5 plus e to the power minus k S3 plus S5 dot, 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 goes on and on. Let's call this as equation number 6. If you compare equation number 6 to equation number 5, let's compare 5 with 6. So let me write down 5. What was 5? 5 said Q of nk is equal to summation S1, S2, S3, all of the spins. The even ones are not explicitly removed. E to the power k S1, S2 plus S2, S3 plus dot, dot, dot. So that is the same as saying S1, S2, S3 e to the power k S1, S2 multiplied by e to the power k S2, S3 e to the power k S3, S4, right? So if you compare 5 with 6, they don't look very similar, right? It's complicated because in this one, you had just a product of two spins, S1, S2, then again followed by product of two spins, S2, S3. This looks something different. So we were able to decimate the even numbered spins. We have reduced the number of degrees of freedom from n to n by 2, but we have landed with a partition function that is even uglier. It's horrible to look at. What is this partition function? It's so complicated, right? Because there is e to the power plus e to the power minus every term, and then this S3 shows up in a complicated way in different terms, right? There is no hope. What have we done? Why have we even done this? However, let me make a claim. In equation 6, if, and this is a big if, we could write down e to the power k S1 plus S3 plus e to the power minus k S1 plus S3. In fact, let's not just think about S1 plus S3. Let's think about any pair of two spins, S plus S prime, because that is the general form, right? S plus S prime. If we could take this thing and write it down as something that looks as a function of k multiplied by e to the power k prime S prime. If we could do this, then what would equation 6 look like? Then equation 6 would be equivalent to writing q of n comma k prime. Okay, the interaction is now given by some k prime. We don't know what k prime is. We don't know what f is. We don't know what is f. We don't know what is k prime. We have to figure this out. And we don't even know if such an equation can be written down. But if it was to be written down, then this q of k comma n comma k prime would become summation S1, S3, S5 e to the power k prime S1, S3 e to the power k prime S3, S5 e to the power k prime S5, S7. And up here, you would have to multiply by f of k to the power n by 2. Now, equation number 7 does look very much like equation number 5. there is a f of k to the power n by 2 multiplied before the summation. I think we should not, let me write this down, write down this equation on the next page. So I just showed that, let's call this equation 8 and let's call this as equation 7. If 7 was possible, what do I mean by 7? i.e. e to the power k s plus s prime plus e to the power minus k s plus s prime was equal to f of k e to the power k prime s s prime for all possible s s prime. What does that mean? That means 4 values. It means s s prime is equal to +1 minus 1, s s prime is equal to -1 plus 1, s s prime is equal to +1 plus 1, s s prime is equal to -1 minus 1. So 4 possible cases. If we could do this for 4 possible cases, then equation 6 leads to equation 8, which is q of n comma k prime is equal to f of k to the power n by 2 summation s1 s3 s5 e to the power k prime s1 s3 plus s3 s5 plus dot dot dot. This equation number 8 is just like our Ising Hamiltonian, the partition function for the original Ising Hamiltonian, which was our equation number 4, right? If you look at equation number 4, it had k s1 s2 plus s2 s3 plus s3 s4. This is very similar. You don't have s2, but it is the same, s1 s3 plus s3 s5. It is as if you were sitting in a classroom. I could make this analogy better. You know, it's like you're able to talk to the person sitting one bench away from you through an interaction, completely ignoring the person in the middle, and the Hamiltonian is just the same, apart from this term in the beginning. Now, just to make sure that you are all with me even at the end of this semester, why does this term matter or not matter? This f of k to the power n by 2, will it matter for thermodynamics of the system? Any ideas? Come on, you can help me with this one. It's not too bad. How do I get thermodynamics out of the partition function? Smithan, what do you think?
I'm not, off the top of my head, I'm not too sure. I mean, you would, sorry?
Yeah, go ahead.
Yeah, I mean, you would have to take derivatives depending on like what you want to find.
Sure, but even before derivative, what is that one mathematical function that always shows up while connecting StatMech to thermodynamics, starting with macrocanonical ensemble?
Yeah, you have a ln of something.
Log of something. There we go. So once we do log of q, it will be left with n by 2 log of f of k plus log of this summation, right?
Yeah.
And now comes the other thing you said. In order to get thermo from this, I'm going to be differentiating it with respect to things like beta, right? When I differentiate it with respect to things like beta, this first term, how much will it contribute? 0.
Yeah, nothing, because there's no beta.
Yeah.
Yeah.
Or, well, when you differentiate it with respect to n, it won't. Let's be careful here. When you differentiate it with respect to n, it won't contribute, right? Because no, it will contribute. It will contribute with respect to both. And I'm actually incorrect, because think about k. Even k has a beta.
Oh yeah. It
right. Does have a beta. So I was taking you down a wrong rabbit hole. Well, okay. It is a similar looking Hamiltonian. It's not exactly the same. Okay. Let's remove this line of thought. The Hamiltonian looks similar. It's not exactly the same. And in fact, we might have to worry about this thing upfront. Even log and differentiation might not help us, as we just saw, right? But otherwise, hopefully you will all agree that this equation 8 looks much simpler than equation 6, right? Equation 6 was very, very messy. Many big things multiplied with respect to each other. Equation 8, all of those have come up front, and the term inside the summation is quite simpler. And we just showed that our log trick is not going to help us because k actually does depend on beta, and you have n by 2. So we have to be careful. But let's see how we go from here. But even before we are able to make use of this, we have to first show that equation 7 is indeed possible. If equation 7 is not possible, then it won't work. So we have to do that. We have to work through that. But before we do that, take my word that equation 7, we'll see in a moment that equation 7 can indeed be solved. And this, we can indeed find what is this function f of k. We can find what is k prime. But the nice thing, actually, let's do that before I try to give you more intuition. You might get lost. So let's do that. In order to do that, we have to write down equation 7 for all these possible four values, 4 possible pairs. So what are the numbers? So this is equation number 7. How many unknowns do we have in equation 7? 2 unknowns, right? In equation 7, number of unknowns is equal to 2, right? F of k and k prime, because k is known. We want to solve for f of k and k prime. And number of equations is 4, given on the various possible values of s and s prime. Can we solve for 2 variables in 4 equations? Looks like we will be in trouble, right? But why does this happen? Why can we still do it? You will realize that these 2 lead to the same equation, while these 2 lead to the same equation. You can write down and see. So let's do that. Let's start with this first one. S comma s prime is equal to plus minus 1. If we do that, what will we get? So if s is equal to plus 1, s prime is equal to minus 1. Equation 7 becomes e to the power k, s plus s prime is 0, plus again e to the power minus k multiplied by 0 is equal to f of k e to the power product of s prime is minus 1 e to the power minus k prime. Or what did we just do? We just showed that 1 plus 1 is equal to f of k e to the power minus k prime, or f of k is equal to 2 e to the power k prime. So if we knew k prime, we could solve for f of k. It is simply given by e to the power k prime. So we got one answer. Now, if we go to the second equation, if we write s is equal to minus 1 and s prime is equal to plus 1, we get exactly the same thing, right? Nothing changes. Gives again the same equation. You can see for yourself, because this will still be 0, this will still be 0, and product of s comma s prime is still going to be minus 1. So we land with the same thing. Now let's go to s is equal to plus 1, s prime is equal to plus 1. What do we get now? We get e to the power s plus s prime is now 2, e to the power 2k plus e to the power minus 2k is equal to f of k, and now s and s prime have the same sign, so e to the power k prime. And when s is equal to minus 1 and s prime is equal to minus 1, then this becomes s plus s prime is now minus 2, so this becomes e to the power minus 2k plus e to the power 2k is equal to f of k e to the power k prime. Again, the same equation, right? This is just a plus b versus b plus a. We haven't changed anything. So our 4 equations in 2 variables actually led to 2 equations in 2 variables, and now we can solve for this. Let's call this as equation number 9a, and let's call this as equation number 9b. Solve 9a and 9b for k prime and f of k. Okay, that's the plan. So how do we do that? So what was 9a? 9a told us f of k is equal to 2 e to the power k prime. And 9b told us e to the power 2k plus e to the power minus 2k is equal to f of k e to the power k prime. So let's solve this. Let's first solve for k prime. How do we solve this equation? What can we say? So 2 e to the power 2k prime. How do we solve this?
Do you just write it in terms of cos h?
How do you introduce cos h? Tell me. What is the
Because-
definition of cos h? I forget.
Sorry?
What is the definition of cos h? I keep forgetting.
Shouldn't it be
E
cos
to the x plus e to the minus x by 2.
So you are saying, let me look up.
I mean,
remember.
I don't see if we can do anything else with it. So
Yeah, sure. I never remember hyperbolic formulas, but yeah. So what Smithan is saying is that cos of x is e to the power x plus e to the power minus x by 2, right? So e to the power 2k plus e to the power minus 2k by 2 is hyperbolic cos of 2k.
2k. Yeah.
Everybody agrees? Okay, great. So e to the power 2k plus e to the power minus 2k is equal to 2 hyperbolic cos of 2k. Therefore, we have f of k is equal to 2e k prime, and 9b becomes 2 hyperbolic cos of 2k is equal to f of k e k prime. So, okay, now what should we do? We would like to solve for
If you plug the f of k in this, you should get a 2 on both sides get cancelled out, and you should get cos h of 2k equals e to the 2k prime.
So yeah, you want to put f of k over here, right?
Yep.
So 9b implies that 2 hyperbolic cos of 2k is equal to 2 e to the power k prime. We just put it here, multiplied by e to the power k prime. So hyperbolic cos of 2k is equal to e to the power 2k prime, or k prime, or if you take log of both sides now, then we get log ln of hyperbolic cos of 2k is equal to 2k prime, or k prime is equal to half ln hyperbolic cos. And before you think this is terrible, this is just the worst math ever of the semester. Something very nice and intuitive will come out in a moment. So just hang in with me. Okay, so we just got k prime is equal to half ln cos of 2k. And then we can write down f of k. From this, that will be 2 square root of cos of 2k. Correct? Let's call this as 10a and 10b. What have we just achieved over here? We have done something quite interesting. We have written down what was k. Our k, remember, what did we start with? Our k was j divided by kbt. We have just written down that if we decimate half the spins, what will be the value of k prime in that system? Let's call it j by kbt prime. You know, everything changes in that system. We have just shown that we can calculate the value of the coupling in this new Hamiltonian, the k prime factor, from the original Hamiltonian by just solving this equation. And we can also calculate the thing upfront by solving this equation. So there is a pathway that we have not just shown that the Hamiltonian for the system after decimating these, where did my decimation picture go? After decimating these even number spins, which is averaging after this, a Hamiltonian does indeed look very similar to the full Hamiltonian for the full system, with the difference being that you have this thing up front, which we saw, we cannot ignore, we have to worry about it. But the interaction term, the summation over all spins, is just like the original spin. So the system has not really changed its physics in 1D. You can already see what's going on here, why we might not get phase transitions, because the system's physics does not change. And it will become clear in just a moment. So this is 10A and 10B. We have to do a bit more work before we can derive what is known as the central RG equation. Any questions about this? Okay. So again, read Kardanov's paper for American Journal of Physics. It's really, really well written. It's a wonderful paper. So what we are really interested is in the partition function, right? We are interested in Q of K comma N, because we were just talking about how Q of K comma N or K prime comma N, we can take its log and differentiate it with respect to something to get averages. We can differentiate it twice with respect to something to get fluctuation, right? That's the big picture of StatMech. Differentiate one, you get once, you get first moments. So let's go one step back. The big picture of StatMech is to take a log, then differentiate once to get thermodynamic averages, and differentiate twice to get fluctuations. That's really the big picture. So we can do all that if we know the partition function. So this partition function, if we divide it by n, if we take the log of the partition function, then we know it is some sort of free energy, correct? If we divide it by n, then we can introduce another term called g, and this g will now be a function only of k, not of n. Any ideas why? Michael, you want to help me here? Why is g not a function of n?
I'm kind of stuck.
No, let me help you. I know this is kind of abstract, but let's work through it together. So I told you that when we take log of q, hopefully you remember this, it's a free energy, right? What do we know about free energy? Is a free energy intensive or extensive? Does the free energy, what does that mean? It means if you double the size of a system, the free energy doubles. What is n? Is n intensive or extensive? If you double n, what happens to n? It's the most extensive you can imagine, right?
Right.
What happens when you divide an extensive thing by another extensive thing? You get something which is intensive. So yeah, don't feel bad about this not coming to the top of your head immediately. It's kind of abstract that we forget, but hopefully you remember it. This is like a common concept in thermo also. When you divide two extensive things, you get an intensive thing. So g of k is intensive. Thanks, Michael. G of k is intensive. It does not depend on n. And this g of k is basically an intensive free energy. And that's what we are going to be interested in. And we can get all sorts of thermodynamic properties also from g of k. We can get heat capacity, we can get all sorts of molar properties out of this, right? Because often we are not interested in what happens with the size of the system. We are interested in things in thermodynamic limit per average number of atoms. Okay, so with this, let's look at equation number 8. What was equation number 8? Equation number 8 says that Q of n comma k prime. Again, if this renormation group stuff seems abstract, I'm with you. You don't get Nobel Prize for something just like that. You know, it's a complicated idea, but it's really, really beautiful. And I'm trying to teach it to you on the last class, even though it's not on any homework, is because for many of us, even if you're doing theory, but especially if you're not doing theory, you might not get a chance to get introduced to renormation group theory, which is so closely connected to Maryland chemistry. And it's one of the beautiful ideas, one of the most beautiful ideas in StatMech. So this is our chance to look at it together and at least get a picture of, you know, one of these most beautiful ideas in science. So now equation 8 was Q of n comma k prime is equal to f of k to the power n by 2 summation S1, S3, S5, e to the power k, S1, e to the power k prime, sorry, S1, S3 plus S3, S5 plus S5, S7 plus dot, dot, dot. Okay. So we can write this down as Q of n comma k prime is equal to f of k to the power n by 2. And this thing over here is nothing but Q of n by 2 comma k prime, right? Does that make sense? That is the partition function for the original Hamiltonian. If this confuses you, go to equation number 4 and think about it. If in equation number 4 you had half the number of spins, and if instead of k you had k prime, then you would get Q of n comma k prime, right? So if this confuses you, look at equation number 4 with k going to k prime and n going to n by 2. So let's call this as equation number 11. Let's take log of equation 11. Let's log 11 on both sides. Then ln q of n comma k prime is equal to n by 2 ln of f of k plus ln of q of n by 2 comma k prime. Okay, now if I divide by n, if I divide both sides by n, I do 1 by n ln of q n comma k prime, divide this one by n, that becomes half ln f of k, and this one I divide by n ln q of n by 2 comma k prime, but here I have an n by 2, so let's multiply, divide by half, let's introduce an additional 2 in the factor. So what do we have? Suddenly we have a very interesting relation. Now we have something for the free energy, for the system size independent free energy, which says g of k prime is equal to 2g of k minus ln well, okay, let me not jump through this. So on the left hand side, I have g of k prime. Oh, I missed something. Oh, does anyone see what I missed? What is the mistake in this equation? This one has a mistake. Okay, it might not be that obvious. Let's look at it again. So the mistake comes from this. It was actually one step. This was q of n comma k, right? In equation 6, the left-hand side of equation 6 was q of n comma k. We are still talking about the partition function of the original system. So this thing should not be k prime. This thing should be n comma k. Okay, that was the mistake. So that doesn't affect here, but it does affect this one. So this is n comma k. Now we will be okay. Let me remove this, sorry about that. Right, because this is the in an interaction in the system with n spins and k. And how does that connect to interaction in the system with n/2 spins and interaction k prime, right? That was the equation. So that's what we were missing. So if we take log on both sides of this, then ln of q n comma k is equal to n/2 ln of f of k plus ln of q n/2 comma k prime. Now I divided by n both sides. So 1 by n ln of q n comma k. So this is one of those cases where you have to be very careful with writing down the, in general in StatMech, it's a good idea to write down what are the variables that your function depends on. So, and this is half, especially because some books use z for partition function, some use q, some use omega. As long as you if you specify what are the variables on which the partition function depends, you're all good. Plus divided by n, but I will introduce another half over here, ln q of n/2 comma k prime. This thing on the left is g of k. This thing is half ln fk, and this is half g of k prime, right? Therefore, g of k prime is equal to 2g of k minus, we multiply both sides by 2. So 2g of k minus ln f of k, and we calculated f of k right here in terms of k. So this gives us g of k prime is equal to 2g of k minus ln of 2 square root of hyperbolic cos of 2k. And this is the key equation of renormalization group theory. This one is called the central RG equation. Let's write it down on the next page and meditate over it for a little bit. So we just derived the central RG equation, which tells me the intensive free energy. It removes the effect of the scaling of the system size, which is something you can do if you're in thermodynamic limit. If you divide by half, you still have a lot of things. That's the idea. So it tells us that g of k prime is equal to 2g of k minus ln 2 square root of hyperbolic cos of 2k. Why is this one called the central RG equation? Anyone sees already why is this equation so powerful? Why is this called the central equation? What does this allow us to do? No, not obvious. What this allows us to do is to start with a k prime that is very small. Okay, you can make it 0 or something very, very small. What is the meaning of k prime very small? K prime is j divided by kbt. So k prime very small means j is very small or t is very, very large. If k prime is very, very small, close to 0, what can you tell me about the partition function of a system made up of n spins where the interaction between the spins is very weak or almost none, and there is no external field? Can you tell me the partition function for that system? There is no math, there is no calculation here. You should be able to write it down without any problem. In order to do that, your hint is equation number 4. So think about equation number 4 when k becomes very small, 0. Let's make k 0. What is the value of q then for a system with n spins?
right? The whole sum become 1, and then n number of things becomes n.
Almost on the right track, Kishla. You are correct that everything contributes 1, but how many terms do you have in this summation?
You have n terms, right?
No. How many microstates? Let me put it this way. How many microstates can an Ising model take if every spin can take 2 values?
Two to the power n.
2 to the power n, there you go, exactly. And each value, each contribution is 1. So this is why this is so wonderful. If k is very small, if k prime is very small, then q is 2 to the power n. You can write down the partition function exactly, right? There is nothing going on here. There is no temperature dependence because the system is made up of spins that don't talk to each other. So if q is 2 to the power n, then what can we say about g? G at 0. So this is true for k being 0, right? Numerically, it does not help if you take k is equal to 0. We do a bit of cheating. We say, let's say the interaction is very weak. So let's say this k is 0.01, which is actually a bit different from 0, but let's say it's still close enough. So what we are saying is that g of 0.01 is going to be approximately 1 by n ln of q. What is ln of q? Ln of q is n log 2 by n, or ln 2. So g of 0.01 is approximately ln 2. Okay, what do we do with this? We have this. So k prime, we also derived an equation connecting k prime to k, right? So we wrote that k prime is equal to half ln hyperbolic cos of 2k, right? This is when Smriti helped me with the hyperbolic cos. So what does this mean? This means that k is equal to half. Let's not rush here. So this means that two k prime is equal to ln hyperbolic cos of 2k or e to the power 2k prime is equal to hyperbolic cos of 2k, or 2k is equal to hyperbolic cos inverse of e to the power 2k prime, or k is equal to half hyperbolic cos inverse of e to the power 2k prime. So if you put k prime is equal to 0.01 in this equation, then you can now write down the value of k. You can get the value of k by using a calculator or Wolfram alpha or something. It's going to be hyperbolic cos of e to the power 0.02, which comes out to be approximately 0.100334. This is something I computed beforehand. So this all might seem a bit messy, but let's see what we have done here. What we have achieved over here is we started with a certain k, very small. We would have liked to make it 0, but for numerical reasons, why you see the numerical reason here, right? Because if you had put k prime is equal to 0, then you would have had a problem. Things would have blown up. So you start with k prime, which is very small. You started, and the k prime is changing to k. So the notation between k and k prime might be confusing. We can just call it k. So we start with k is equal to 0.01. In this case, our renormalization group theory based G, the free energy. How much was that? We said that, well, 0.01 is such a weak interaction that we can just assume it's close to 0. When it's close to 0, the partition function is 2 to the power n. When partition function is 2 to the power n, that means the intensive free energy is log 2 approximately. So our starting point is that the intensive free energy is log 2. Now we can put this k in this equation and calculate another k from this, right? The other k value comes out to be something larger. It is 0.10034. So we are going in an opposite direction. We just showed the derivation that we did was to start with a very big system with lots of interaction and keep reducing the number of spins. We are here starting with a system with very weak interactions, taking the value of k, which corresponds to very weak interactions, plugging it in our self-consistent equation for renormalization group, and getting the value of k. Using 0.01, you get the value of 0.100334. However, we still need to calculate the g for this value of k. Do we know how to do that? Yes, we do. We can calculate the g for this new value by using this equation, right? So we can plug in the value for k over here. So, and then calculate our value of g of k, and that comes out to be 0.698147. So what did we do here? We used, wait, I did not give a name to my central RG equation. That's terrible. So this equation is equation number 12. We used the central RG equation using central RG equation. Now we can take this k of 0.10034, and instead of this e to the power 0.02, we can put in this new value of k and solve it to get another value of k. If we do that, you will get the value 0.327. You can again use the central RG equation and you will get a free energy, which will be something else. I did not do this one. And you can keep doing this. Once you keep doing this, the value of k keeps increasing, which means you started with a system where there was no interaction. The value of k keeps increasing. You go up to something like 2.702196. This is one of the values you will get, for which the value of this renormalization based g, and again to remind you, this is g of k, there is no n over here, comes out to be 2.706633. In the right, I will write down the exact number. This is Ising model in 1D. You can calculate everything exactly. So when you calculate this for 0.01, you get a value 0.693197, and the value of log 2, by the way, is 0.693147. So there is some error at the 5th decimal place. If you go further, you see it comes out to be 0.698172. The error has decreased. And as you keep going down, it becomes more and more exact. There is no reason to stop here. You could keep increasing k. And remember, increasing k is equivalent to decreasing temperature, right? So you can keep increasing k, or you can keep decreasing temperature. You can start from k is equal to 0, and you can use this operation to reach any value of k as large as you wish. By doing this operation again and again and again, you won't have any interruption. You want k is equal to 1 million, just do this iteration a few times and you will land somewhere in the vicinity. If you landed a bit off, start with a slightly different value in the very beginning, and you will land close enough. So you can start from k is equal to 0, you get to k is equal to 0.01. Well, we actually started from 0.01, you get to k is equal to 0.1, you get to 0.3, you get to 2.7, and it will keep going so and so. So this here is called a flow diagram. It shows you that in 1D, you can write down the system for very weak interaction and keep using the central RG equation and get to K as large as possible. Indeed, this flow diagram is what we called uninterrupted flow. The physics of the system is independent of what value of K do you take. Okay? The same Hamiltonian, the same equation 8 that we wrote down, a simple equation 8, is applicable for any value of K. This is what leads us to conclude that there is no phase transition. A phase transition would have meant that you start from some value of K and you get stuck. Your iteration stops at certain value, and beyond that, that value would then correspond to the value of the critical temperature. Something discontinuous happens in the system. So in 1D, all of this math that I did, for which I think for probably everyone is very new, you're seeing this for the first time. It seems also complicated. If you go through it, it's not that complicated, but the answer is kind of obvious. We had already seen it through something as simple as the Pearl's droplet argument. There is no phase transition. In 2D, this becomes more interesting. In the next 8 minutes, I'm going to do all of this for 2D. No, just kidding. I'll give you the picture of how it is done in 2D, and I will show you how the flow diagram looks in 2D. Read through Kadanoff's paper. He does a better job of explaining, I think, than I did, or maybe not. In general, these things take a couple of iterations to understand. It's hard to get it in one go. At least I did not. So if you go to a 2D Ising model, now the decimation will look a bit different, right? What is the meaning of even number and odd number? It's a bit complicated. So this is a 2D square lattice. Here we are going to decimate these spins. If we do such a decimation, then what's our remaining system? It still looks like a square lattice, right? So just like in 1D, when you did decimation, it still was a 1D lattice, right? In 2D, when you do the decimation, after decimation, it is still a square lattice, but rotated by 45 degrees. But that rotation doesn't really mean much. It's just bookkeeping. Half the spins are gone. So I think Chandler 5.7, let me check. There's no more homework, so I won't give this to you, but you're most welcome to go and try it yourself. Is it Chandler? No, it's not Chandler 5.1. Just read the article by Kadanoff, which I posted online. Kadanoff goes through this, does the whole system, writes down a new Hamiltonian for this decimated system, solves for different value of the spins, self-consistency, and comes up with a flow diagram. The flow diagram in 2D, however, looks interesting. You again start, so this is Kadanoff, American Journal of Physics. You again start K is equal to 0, and this will take you to some larger value of K, which will take you to some larger value of K. However, you will find that there is a particular value of Kc at which you get stuck. Once you reach this value of Kc, unlike in 1D, where the value of K kept increasing further and further and further, in this one, it plateaus and stops at a certain value of. So how does a stop sign, I'm trying to see, look like? I've forgotten. I haven't driven a car in a long time. So this is how a stop sign looks like, right? You can't go further. Your algorithm brings you that value of K and you stop. You could do a same thing, and you could do the similar thing in 2D by starting from K is equal to infinity. You could start from a system where you solve for K is equal to infinity, and there you would keep coming down to this value of Kc. And Kadanoff shows this, that one comes at stop again at the same value of Kc. So this value of Kc, or J by KBTC, is then the value of the critical temperature. Kadanoff does it for a square lattice, and the value he gets is 0.50698, while the exact value is 0.44069. And so it gets it quite right. most importantly, it's better than mean field theory, because mean field theory simply got a wrong critical temperature. It told you there is a finite temperature, while in 1D, you do see the flow is uninterrupted, and this, which means that there is no critical temperature. And in this one, we have an interrupted flow, and the value at which the interruption happens is the critical temperature. I want to mention just one more point. In mean field theory, you can also take this G of K and expand it in some sort of Taylor series or things like that along Kc. From this, you can get the heat capacity, right? Because if you can expand the, if you can write down the free energy as a function of temperature, and writing G of K as a function of K is the same thing as writing the free energy as a function of temperature, then you can differentiate it to get the heat capacity. And this shows us that the heat capacity is given by something called, given by a function that looks like proportional to 1 minus T by Tc to the power minus alpha, where this alpha is around 0.131. And this is the final thing, last thing that I will mention in this semester, and then we are basically done until recap. If you plot this, this is the most bizarre thing about phase transitions. If you plot the heat capacity versus temperature, they stay normal, and then at the critical temperature, they blow up. This is the critical temperature. And from the other side, also, they can blow up like this. And there can be different plots, and often phase transitions are characterized by how these heat capacities blow up. How do they diverge? For such models, the heat capacities tend to go as T minus Tc to the power some minus alpha. These are called power law divergence. These power laws are unanimous with renormalization group theory. They are unanimous because, as you saw, renormalization group theory is really a theory for things that are self-similar, right? You zoomed out and the physics did not change. What is the, in common popular science, does anyone remember what is the word for self-similar things? Fractals, right? Fractals are the best example of self-similar things. And the most common notion to describe fractals are power laws. So it all comes and connects. In 3D, you can show that for a 3D Ising model, this alpha is 0.125 exactly, I think, which is kind of amazing. In 2D, renormalization group theory in Kardanoff's paper shows you there is a value of 0.131, and it allows you to calculate this alpha. So this alpha over here, Cp proportional to T minus Tc to the power minus alpha close to Tc. This is quite a generic property of phase transitions, and this alpha is called critical exponent, which characterizes the power in the power law. And a lot of physics over the last, or chemical physics over the last many decades, has focused around calculating these critical exponents. The nice thing about these critical exponents is that you could be using, in your homework, I have asked you to think about a problem in your research, past, present, or a future problem. You can just concoct one problem, something you would like to work on, which can be described using Ising model. So you could be describing a polymer using an Ising model, a crystal using an Ising model, neurons in the brain using an Ising model. The critical exponents will be the same. They are universal. And this gets physicists very excited because they think, oh, maybe it's the same physics. If you can go and measure the heat capacity and study how it diverges as a function of temperature, you are often looking at the same underlying physics, even though the system is very, very different. This is really the final topic in the semester. Like I said, renormalization group theory could be done. I didn't even tell you what's the group here, what's the group theory here. You know, there are a lot of things you could study. Read the Kardanoff paper if you want to read more. There is too much, a lot of literature on the internet, including the Nobel Prize lecture by Wilson. You can go and read that. And so next class, I'm going to do a recap of the full semester, the key ideas that I hope. There is no exam, so this recap is not going to help you with the exam. That is not. If you don't show up for last class, I will be a bit sad. I will be very sad because I would like to walk through the semester, look at the basic concepts. People like Shams and some of you are going to use StatMech for the next many, many years, so you will deal with them all the time. For those of you who might not do StatMech for your bread and butter, for your living, you should still remember these concepts. And another very important point, the course eval for this semester is open. You should have received a link about this. Please go and fill it up. I will be going up for tenure this summer. My tenure depends on whether you all give me feedback or not. Hopefully not too negative, but if it is, then what can we say? Your feedback is important to me also to improve as a teacher. I get a lot of feedback every year, and I've tried to become a better teacher through that. So please take the time to fill up this course eval. It finishes in like a few 2-3-4 days. So it's anonymous. Your name is not revealed to anyone. So you can tell me, and we will keep it in compared to other classes that you're taking. I know, and in general, you can tell me on Slack how I could have improved. What are the things you like? What are the things you did not like? This is my 4th time teaching it. So I'm not going to teach it next time, but I'm sure I will teach it again in the future. And in general, it's good to know how can one become a better teacher. So any questions about renormalization group? Okay, if not, please take the course eval and post questions on Slack. That will help me cover. If something is confusing, I can talk about it specifically in next class. And you have one homework and one final exam due. I hope you enjoy that. Otherwise, hope to see you on Thursday for the final class. Bye-bye.